So now let's start drawing Bode plot. So first magnitude plot. So initially we have seen at omega less than omega p, omega equals to, this is omega p, so this is 0 dB, and after that omega greater than omega p, there is a roll of minus 20 dB per decade. But actually this is not like this, so this is something like this, and this point at omega equals to omega p, this is minus 3 dB point, and at this line this is 20 dB, minus 20 dB per decade roll off. If we consider say omega 1 here, omega 2 here, and omega 2 is 10 cross of omega 1, then this magnitude difference is 20 dB. Okay, now let's draw phase plot. So this will be something. Okay, let me draw it some more accurately. So this is 0 degree, this is minus 45 degree, this is minus 90 degree. So this point, which is minus 45 degree at omega equals to omega p. Why? So at this point phase change is given by omega p. Now omega equals to omega p, omega equals to omega p, so this is hyphen tan inverse 1, which is equals to 45 degree, and one pole give pole shift of 90 degree. So this is all about frequency response. Now let's consider one example. So let's consider one example. Now suppose we are having a circuit with gain ADC, then there is a RC circuit, this is R, this is C. So this is considered as a single pole system, or you can consider it as a whole as a amplifier with single pole system, which is having gain of ADC and pole is that RC. So frequency response is given by ADC divided by hyphen S upon omega p, where omega p is equals to 1 by RC, minus 1 by RC, and we have seen this is 1 by tau, tau equals to RC time constant. This is time constant. Now for this let's consider 3 cases, and yeah, in this we will also find out relationship between ADC, DC gain, omega p, and omega UGB. So UGB frequency is unity gain frequency. It is known as where DC gain goes to 0 dB or magnitude become 1. So that is basically a UGB frequency. Now let's consider case 1, when omega much less than omega p. So magnitude is given by in dB. So in dB given by ADC divided by square root of 1 plus so this will be 20 log ADC square root of 1 plus omega upon omega p square. Now omega upon omega p much less than 1, so HS dB equals to 20 log ADC. So we can consider this as a ADC in dB, say. So at low frequency our magnitude gain is ADC. Now let's consider second case 2, when omega equals to omega p, omega upon omega p equals to 1. So magnitude response in dB is given by again 20 log ADC upon 1 plus omega upon omega p square. Now this term is 1, so 20 log ADC divided by square root of 2. So this is 20 log ADC minus 20 log 20 log square root 2. So this term is minus 3 dB, so 20 log ADC. So this term we can say ADC in dB minus 3 dB. So omega equals to omega p is a point when our gain degrades by 3 dB. Okay, now consider case 3. Case 3 is basically omega greater than omega p, omega upon omega p greater than 1. So this magnitude in dB is given by 20 log ADC square root 1 plus omega upon omega p square. So this can be written as 20 log ADC divided by omega upon omega p, and this further we can write 20 log ADC minus 20 log omega upon omega p. Okay, so now so this is HS dB. Okay, now if we again consider same thing, omega equals to omega 1 and omega equals to omega 2 equals to 10 times of omega 1, then, or you can say omega equals to omega p and omega equals to 10 times of omega p. So after this frequency this term is minus 20 dB, or this term says gain roll off by minus 20 dB per decade. Now let's consider case 4, when omega equals to omega UGB. So it means our gain, okay, HS dB equals to 0, because at this frequency our magnitude is 1. So what does this mean? Because 20 log, if 1 is magnitude, it will come like a 0 dB. So that's why HS dB is 1. So if we put these values in this equation, then what we will get? So 0 dB equals to 20 log ADC minus 20 log omega UGB upon omega p.